Okay, so next we'll take a look at some protocols that describe problems with managing keys more than the actual authentication. So they do involve authentication, but it was more a problem with what do you do with these keys? So the first one we look at is the offline PIN problem. There's a similar problem actually described in the book, but this is a slightly different problem than in the book in chapter 3. So IBM had this system for ATM machines where what they would do is they would generate a PIN number based on the primary account number using a that's encrypted using a key. And so what they would do is to make these ATMs available even when um, the ATMs were offline, that is not communicating with a bank server, which happened quite a bit. In the old ATMs, it's no longer a problem, but in the old ATMs, it would actually be using a modem, so it would actually call over the telephone lines and send information to check if someone entering their PIN was, entering in the right PIN and all of that. But these machines, way back then, would go offline, and then um, what IBM decided to do was write this PIN number encrypted using a common key to the magnetic stripe on the card on one of the tracks, and then give the KA, that is the key, to all ATMs. Well, a bunch of problems with doing this. You don't want to be doing this, but for one thing, you could copy the magnetic stripe, and there was a lot of attacks that used that. Um, Another thing that happened is the fact that you can now that key was now stored in the ATM, which you probably shouldn't do. Once the crooks found out in about 1993, there was a lot of problems, and there was a huge increase in the number of crimes involving ATMs, and offline operations had to be suspended. They could just they couldn't work offline because there were just so many problems. So we'll see more examples of these kinds of problems and security protocols in the chapter on banking and bookkeeping. Okay, so let's do one more example. The next one is the chip authentication program. So this was a scheme that the banks in the United Kingdom were trying to use to stop phishing. So each customer of the bank would get an EMV chip card reader. So EMV stands for Europay, Mastercard, Visa. They came out with actually if you have a chip in your credit card, it's this kind of scheme. So it was adopted early on by UK and Europe in general. And at one point in time, they tried to give out these chip card readers to bank customers. There was an easy mode where the customer uh, gave the PIN number. So this would be a device that you have at home, let's say. You would enter the PIN number, and then the reader would send back to the customer some information, which was essentially the nonce and the PIN number encrypted using some key. And so this encrypted message was used to authenticate with a bank, let's say. So the user gets the string, and on the other hand, besides the device, let's say you're authenticating online or by phone with the bank, and you would just punch in this encrypted string or read it out over the phone. And there were a lot of problems with this, and this is described in the book, but you just want to see this, how this protocol or this program is described using our protocol notation. There was a serious mode too, that is where if you are, let's say, trying to use your account to pay for something, not only would you have the PIN number and this nonce, but also the amount that you were trying to pay off, and the last 8 digits of the account number of the person that you were paying, all this other information. It was all encrypted to avoid things like replay attacks. So if you look at this easy mode was susceptible to a man-in-the-middle attack where people were snooping and listening on your conversations online. Okay. Next one is the HomePlug AV key management scheme. So HomePlug AV was a power line communication system. So you would plug these things into power lines, and they would use the power line to communicate between devices. So you would send something like Ethernet. It's not exactly Ethernet. It was a totally different protocol, but it would send out these signals using your power line. So on top of your power signal, there was also this communication scheme. It had a secure mode where you type in the device key KD from the device label. So you look on the back of these devices, there would be a device label. You put that into the hub, and then the hub would send the device an encrypted master key using the KD device. So this was probably secure, but there was also a simple connect mode where the hub sends the device key in the clear to the device, so without encryption, and then the user just confirms whether it's working. So this was optimized for usability, so a user doesn't have to read this number from the back of the device, punch it in, all of that. And so the simple connect mode was usable, but it was not secure. And that was the problem that that a lot of people ran into. If someone was listening, or if someone knew the device ID, it could be the supplier itself, or someone who's delivering this could just take a peek and look at the device ID, and then they could basically break into your communications at home. Okay, so there's a lot of problems having to do with managing keys, and so we'll look at that in a little bit more detail. Let's take the general key distribution problem. So the problem is, and you'll see this a lot in the chapter on cryptography. You have two principals, Alice and Bob, and as the book says, these are not, you don't want to take these as actually people. They're just principals, principal A and principal B. They could be programs, and they want to communicate securely. They want to use a trusted third party, and we'll call this SAM, and usually it's a server S, or let's call it SAM for this example. And so what they want to do is have a common key for cryptography. How do you solve this problem and make it resistant to things like replay attacks, all of the things that we've seen so far, man-in-the-middle attacks? So if someone is listening in on Alice and Bob, or Alice and Sam and Bob and Sam, and if they're able to see all these conversations, can they figure out what the key is that Alice and Bob are going to use? So how do you make it secure even when the communication is not secure? Okay, so the first thing that has to happen is one of these people has to get in touch with Sam and ask for a key for the other person. In this case, Alice calls Sam and asks for a key for Bob. So Sam sends Alice a key encrypted, and so that if someone does actually snoop on this traffic, they cannot figure it out because it's encrypted. And so that's in a blob that only she can read, so only she can decrypt ideally. Of course, if someone who's eavesdropping can read it, can somehow got access to the key and can decrypt it, then the game is up. So assuming that eavesdroppers cannot decrypt, then Sam sends Alice this encrypted blob, and that blob has the same key also encrypted in another blob, only Bob can read. So Sam sends Alice two things, a key, and also another encrypted thing inside that encrypted message that only Bob can read, and then Alice calls Bob and sends that second blob that only Bob can read to Bob, and then Bob will essentially end up getting the key. So this is a basic idea, and this is actually used, but there are problems not so much with the encryption. There are problems with the encryption, but there are problems with the protocol. There are vulnerabilities. Okay, so you want to do, the thing is you want to have this key distribution scheme. So Alice and Bob want to communicate, they want to have a common key. How can you do this in a way that's resistant to replay attacks, man-in-the-middle attacks? And how can they make sure that these messages are fresh and not replayed from a year ago or 2 years ago, things like that? So that essential idea is the key management problem or and so here's a protocol. So here's a possible protocol for solving this problem. It uses timestamps. So this is just a protocol notation version of the stuff that we had described earlier, but you want to make sure that this makes sense, that you want to take a look at this and see if it's resistant to attacks. So Alice sends Sam a message with the identities of Alice and Bob. So these are, let's say, user IDs or whatever. Sam replies with Alice's ID, Bob's ID, and then key that Alice and Bob are going to use, that's KAB, along with the timestamp. And this is all encrypted using a key that Alice and Sam share. So this is something that only Alice can decrypt. And then also sends the same kind of thing in a message that's encrypted using a key that Sam shares with Bob. So they do have to exchange these keys first, KAS and KBS. And then once they have shared those, then Sam sends Alice these two blobs, and Alice sends this blob over to Bob. And then once this is done, then Alice can send Bob whatever message that she really wanted to send. So the actual communications come after. Alice starts sending messages using this KAB that was encrypted. So thing to keep in mind is that you're sending blobs, and these blobs contain keys, and they're encrypted for safety so that no eavesdropper can see this key in plain text and use it to eavesdrop on this traffic. Okay, so we look at a couple of versions of doing this. It turns out this particular approach is not going to work. There are some vulnerabilities, and it's not so crucial exactly what those vulnerabilities are, but just to recognize that this protocol notation is describing this protocol notation is describing this description. Describing this protocol, this key distribution protocol. Okay, so there were quite a few attempts to do this because this is a really common problem, and so there were many such schemes proposed by people. They pretty much all had vulnerabilities. Here's an example. This protocol was proposed by two people, Wu and Lam, and you can click on this link in the PDF to figure out, to get this complete description and see what the problems are. You can see a Wikipedia article about this protocol. And actually, these two authors came out with a number of these very similar ones. They all have problems, it turns out. So this looks like a reliably secure way of solving this problem, but it turns out it does have problems. A big step came about in 1978, so it's 40 years old, and this was created by two people, Needham and Schroeder. And it turns out Needham was the teacher who taught the author of the book, Ross Anderson. So this was our textbooks author's teacher. So what they did in 1978 was they used nonces rather than timestamps. So we can go through this step by step. Alice sends Sam three things: Alice's ID, Bob's ID, and a nonce that Alice created. So Alice is telling Sam, I'm Alice, and I want to talk to Bob, and here's a nonce. So Sam replies to Alice, okay, here's your nonce back in an encrypted message, and here's Bob's ID. Here's a key that the two of you can use, and here is a blob that you can use to send, that you can send to Bob. You can't read it, but Bob can. And this is all encrypted using a key that is shared between Sam and Alice. Okay, so that's the second step. Sam sends Alice a session key that is KAB with her nonce to prove that it is fresh, it just happened, and then and it's not a replay. And then in the message, it's encrypted using a shared key that Alice and Sam share. And here's a certificate. You can call this a certificate, but it's just a encrypted blob that's meant for Bob. So what Alice does next is send that blob, that's just this blob here, to Bob. And then Bob, it's not shown. Remember, this is the thing that about security protocols is that Bob can decrypt this, assuming that Bob hasn't lost this key, and use this KAB from now on. So Bob didn't know what this KAB was. He just got it. Alice got it from the server Sam and sent it to Bob, and now Bob can use it. And it also has Alice's ID to prove that it's from Alice. So then there's a final step where Bob does a quick challenge and checks if it is really Alice by sending a nonce using this new key that Bob just got. Alice will reply. So this is like a challenge, but it's an encrypted challenge. And then Alice will reply by doing some operation. In this case, he was just subtracting 1 from that nonce and replying to Bob using this new key as well. So this checks and makes sure that Alice is still around. It wasn't a enemy or eavesdropper, and Alice is present for this interaction. Okay, so it turns out that Needham Schroeder had vulnerabilities, and people at MIT came up with this Kerberos protocol, which is a revised version of the Needham Schroeder protocol. So instead of a single trusted third party, there are now 2. There is an authentication server that you're logging into, let's say, and another server that you may not actually interact with, but the authentication server will interact with, a ticket granting server. And the other thing that's done in Kerberos was that instead of using nonces, they were replaced by timestamps. The reason for that is that you could have replay attacks that happened like a year after the nonces were used, and it could still work. By using timestamps, then you know that this is using actual time, and this would be one way to make sure that these things were fresh. Okay, so similar kind of thing to the Needham Schroeder protocol. Alice logs into this authentication server AS, gets a ticket with a session key that was encrypted using her password, and then to get access to some resource B, let's say it's a file or another user or whatever that's controlled by the server S, this is what Alice has to do. Send a message. Here I am, Alice, I want to talk to Bob. Sam, or the server S, responds with a timestamp, a lifetime, and a key that you can use to for this session with Bob, Bob's ID. And Bob can be another account or file or whatever, or some resource. And then also sends basically the same thing as Needham protocol, a blob that's encrypted with a key that Bob and Sam share. So that's this thing, this blob inside this big ciphertext. So a ciphertext inside ciphertext. And this is all encrypted using a key shared by Alice and Sam. Next thing Alice has to do is send that message, that blob inside a blob, or ciphertext inside the ciphertext, which only Alice can decrypt, sends that to Bob, along with a timestamp from Alice, so that Alice knows that this part of the interaction is also fresh. And then finally, Bob replies to Alice. Here's that challenge. Bob takes that challenge, TA, bumps it up by 1. Let's say it's the next time point, and then sends that back to Alice using this new key that they now share. So this essentially solves the problem, but there is still a vulnerability. Now we have to worry about clock synchronization. You have to make sure that these machines, that is Alice and the server and Bob and the ticket granting server, they are all perfectly in sync. And this is actually, it turns out, a big problem. You can have systems set up with clocks out of sync on purpose to try to break this protocol. However, as long as you have synchronization, turns out this is not a problem, and variants of this are actually used in Windows. So Windows Server, Windows 10, all of these versions of Windows to communicate and do things securely. They do use this technique, and it works. Okay, so let's stop here, and then we look at very different protocols in the next lecture.